Well, good afternoon, ladies and gentlemen. Welcome to my talk. As introduced, my name is Gari Arutinov. I'm a program manager at Holst Center TNO within the department of Jeroen van der Brand, who has just presented. And I'm leading a team responsible for laser-assisted processes for microcomponent integration. But first, before diving into the content of my talk, I would like to thank the organizers of today's event for giving me an opportunity to present in front of you today our recent developments for specifically MicroLED assembly. Well, let's start. Most of you, if not all in this audience, probably are familiar with the Moore's law regarding the miniaturization of the transistors, but there is also an analogous version for LEDs with the Holst law, which effectively states that LEDs are expected to be continuously getting smaller and smaller, more efficient and cheaper. With regard to the smaller, they are definitely getting smaller, and already in my own lifetime, and I don't have too much gray hair yet, we had a transition from rather traditional packaged LEDs to now mini LEDs. These are the smaller LEDs that are roughly 150, 200 micron, already quite small, which has been already integrated in the devices like, for instance, iPad Pro from Apple. But now MicroLEDs are booming and they are in the spotlight. Those are extremely tiny, already as small as 30 to 50 microns, so thinner than, again, human hair. They are predicted to disrupt the display industry. But we want to understand why, and what are challenges, what are benefits, and what is the future for them. Well, without going into much intricate details about them, I would like to still list a few advantages of micro-LEDs and understand why display industry is so keen in integrating them. Well, as mentioned, they are extremely tiny, right? That's already given, which makes them a very good candidate for transparent displays. On a mid-range or long-range range, even in a high resolution, they are barely invisible for a human eye, so perfect candidate for true transparent displays. We are able to control them on individual base, so on and off, so perfect for low consumption, good for sustainability. Also, we are able to encapsulate them individually, contrary to OLED, making them less prone to the impact or damage or humidity. So good for automotive applications. I think there is already few list here makes it a unique package of the functionalities that explains why industry is so keen in integrating them. You can see nearly exponential growth of patent applications from all kinds of different players. You can see over here very aggressive acquisitions being made from the big parties taking over smaller ones to make a consolidation. There have been a very intimate and closed ecosystem being formed, governed by big display companies all the way through the whole value chain. And last but not least, with the market size predicted to reach already by 2028, reach and cross $70 billion US dollar market. It's a striking number, so it's a great opportunity. Attractive, but it comes also with the challenges. We need to understand what has been preventing us then so far to mass commercialize these micro-LED displays. And for that, we need to realize one thing. So if my phone is there, but imagine a smartphone-sized display that would already contain over 20 million discrete micro-LEDs that needs to be accurately placed across the display. That, for very much state-of-the-art pick and place, will take over a few weeks to assemble one single display. So not feasible for industry, of course. Apart from that, since the components are getting smaller and smaller, not like that, but really like that, these machines are not even able to handle them. And since they are getting also smaller, we are talking about very different ballpark precision accuracy that needs to be arranged. And last, also, a superior yield. So for yield, we need to be on the same page that defect rate of a display, it's accumulation of multiplier of the defect rate of the components on its native wafer, so faulty die on a chip, and actual transfer precision. And then, since these products are based on a component number which are counted in tens of millions, right, each product, then even if we are extremely reliable per each building block, a brand new display would still have a few dead pixels. Well, unless a repair management is implemented. So it highlights that repair management for such displays is the must. So to sum up the requirement first and highlight the challenges is that it calls for a technology that needs to be extremely fast. It needs to be scalable to catch up with the downscale miniaturization of the components. It needs to be extremely accurate. And last but not least, needs to enable not just a fast and accurate precision of the dies, but also enable a repair, so transfer of a dice on demand. So quite a challenging set of requirements, which probably highlights why it has been so difficult to implement. Well, with these, forthrightly, I would like to introduce you with our technology, how we were addressing these challenges. Well, very frankly, we are new kid in the block for this domain. Yeah? MicroLEDs is the buzz, but it has been a buzz for a decade, if not longer. And we've been active in this domain for maybe around 2.5 years. But I'm proud to present to you today already what we are capable of achieving with this technology for MicroLED assembly. In introducing you a fast CT, so it's a fast, accurate, and selective technology for component transfer, among them for MicroLEDs, which is the co-development of our own proprietary release stack that we developed in-house, in combination with a commercial laser source, but important to mention, a low-cost laser source, so it's making the cost of ownership of the tooling also very attractive. Let me run the animation that first explains the process in a nutshell. So we start with a native wafer with the MicroLEDs. They are being transferred to the temporary carrier, pink surface, brings back to our release stack, and there where the magic happens, we realize the transfer of components on demand with the laser shot. So each laser shot triggers the release of one single component. And we have been able to deploy this technology for various component sizes. I would like to show some of the results for this on the next slide. But before doing that, just want to highlight that in order to realize the transfer from our release stack, we first need to bring these tiny components from a native wafer where the fabs have been developing them and bring it to the release stack. Yeah? We have been developing processes around that. That's quite a complicated and meticulous process. But in a view of the time today, I would rather focus on a transfer precision, transfer process from our release stack and omit this part for today. But highlighting that it's an extremely important topic as well. So with FastCT, what are we able to achieve today? Well, first of all, I'd like to highlight that our technology enables accurate release of the component on demand. What does it mean? One single die can be released from the wafer with the laser shot, while neighbor dies are peacefully residing on the wafer, unaffected. So its selectivity is there, but I would like to also show more convincing results with regards to selectivity in the further slides. It's also a fast release, fast, but at the same time non-explosive, so it needs to be accurate. So dies are not flying all over the place, but directed vertically down, because we need to achieve a sub-micron precision eventually, yeah, to be kept in mind. Then, by deploying the same release stack with no modification at all, we've been able to deploy these for mini LEDs, but also much smaller MicroLEDs of today. So the scalability there, and we see no fundamental limit in deploying this technology to sub-10 micron components as well, which will come in the near future. And last but not least, since we are using lasers, it's a digital, so you can create a patterns on demand, whether it will be a writing Holst pattern with a micro LEDs or arranging them in a QR code that sends to my LinkedIn page. Well, that's for fun, right? But in reality, of course, the displays have a certain regular pitch that needs to be enabled. But before that, I would like to show you some of the numbers here with regard to the yields and precision that we can achieve in our R&D environment, in the lab setting. So here are the numbers. We can achieve already 1 micron precision and 1 degree of rotation for the micro LEDs, and quite a high yield in R&D environment of over 99.9% for the transfer precision itself. To appreciate maybe how precise these components are being transferred in non-contact manner, you can see an overlay image of the microscope image of these dice. These are, again, remember, each thinner than human hair. Well, for the displays, depending on applications, they can be VR or IR with a very dense, high-pitch, low-pitch applications, or coarser TV screens where the dice are spaced farther away. So, while MicroLEDs itself on a wafer are densely packed with a fixed dense pitch. So we need to address all kinds of different applications, but the native sources has the same density.
He enables adaptive pitch for placement of every needed die in the right space, in the right sequence, with no need for repitching or stretching.
So as shown in the video, we can enable so-called adaptive pitch, so you can do a densely packed VR or AR applications by no skipping dies, or you can skip few dies in the wafer for more coarse applications. But the question needs to be asked, what do you do with the dice in between? You have to be very efficient, independent of the pitch on the wafer, otherwise your efficiency of the wafer floor space is gone. And for that, what I would like to show that FastCT enables efficient deployment of the whole wafer space in a process shown here.
It enables the use of 100% of a wafer space and is highly selective.
So what you see here that for a very one of the example here with the application that required to skip one die in between on a wafer space, you can in a forced sequential manner utilize 100% of the wafer space for 4 products. But of course you can extrapolate if it's also a more coarse application where you need to skip 2 dies in between, then it will be 9 sequential products. But the message to take it from this slide is that, for instance, the step number 4, it's the last step. Previously, the dice on a wafer has been illuminated 3 times from the neighbors, but nevertheless, we didn't jeopardize the precision. It's equally good as the initial one, so it shows the high selectivity there. With this, it first sums up the main part of my presentation with regard to the transfer, and I hope I convinced you that in a short span that we have been developing this technology at Holst Center, we managed to meet this quite a challenging requirement from the industry, but of course work goes on. We need to mature this and bring it from R&D environment to the pre-industrial setting and then to industrial settings in the collaborations that we run, and more to come. And I'm sure that Japanese companies can play a significant role with this domain. But we need to realize that to make the display functional, transferring die is not good enough. You need to interconnect this somehow. You need to interconnect to the backplane. How to do that? These components got smaller and smaller. I said it already probably 10 times in my presentation, but along with the component size, bond pads have been shrinking as well. So there, it calls for even higher precision printing technologies for interconnect. And conventional technologies fail to do that. The best what you can achieve, maybe it's a 60 micron dots with the commercial technologies, while MicroLEDs themselves are already 60 and smaller. Next to it, component numbers, I already mentioned, immense. Well, bond pad size is twice more immense. So printing technology needs to be also very, very fast. And last, it needs to be also digital, because we need to realize the repair that I have managed. So in summing up, what we need is the fast digital and ultra-high resolution printing technology, which is actually not there. There is the need. We need to fill this gap. And for that, I would like to also present a technology that we've been developing at Holst Center, which is similar in a way, because it combines, again, co-development of innovative proprietary release stack, a different stack, in combination with the same laser source that have been used for transferring of the dice. Let me show the first animation, how the process works.
And the same proven technology can also transfer ultrafine deposits of wet interconnects, like conductive adhesive or solder pastes, with the same laser source, by exploiting structured carriers covered with a permanent, dedicated release layer.
The take-home message from this video needs to be that it's a permanent release layer that we develop. So by shooting the laser, the release layer is not affected, and it's ready to be recoat it again with the interconnect material of your choice, and print another run, so to say. That's one. Second is, for using this concept, we are able to print both classes of interconnect materials that are currently in use, glues, as well as the conventional solder paste. Would it be a SAC solder or tin bismuth, or you name it. But to achieve the accurate release of these tiny dots of the interconnect material and drive them vertically down on the backplane, it's not easy. Yeah? Yes, we have a cavity, we shoot with the laser, but it can easily go wrong. If you shoot with the laser and material gets hit up on an interface, if it's not uniform, material ends up driving elsewhere. Or, even worse, it can explode. I will show you some examples next slides. So for that exactly, our release stack is responsible to make a homogenization of heat flux absorption inside of the cavity and direct these tiny interconnect dots to the right place, to the bond pad. Just to compare and highlight the relevance of it, an example on the left, you see arrays of the solder dots. Those are, in this case, 30 micron dots of the solder paste. And on the right-hand side, if you do the same, from the same cavity, same laser, same material, but without release stack, you will end up with a spray of the solder. That's what you definitely don't want to have. To show you a few examples of what we are able to achieve already today, here is an array of the glues. As I mentioned, we are able to print both classes of materials down to 20 micron, what we are able to achieve today. And for the solders, it says 30 here, but in a very recent time, we already achieved close to 20. And our roadmap to catch up with the miniaturization of the components and these bond pads being shrinking to achieve 5 and 15 micron respectively for glues and solder pastes. More examples here. This is an array of the solder type 7 solder paste of 30 micron dots. And if you look into individual dot, you can actually count only few solder dots, solder balls. So that's how challenging it is to maintain the clean deposit. And keep in mind, it's a low-cost type 7 coarse material. We're not talking about extremely fine solder paste. And we believe that going to the unique materials, and there's lots of development for solder paste as well, going type 8 or type 9, we can drive this resolution down to close to 15 and maybe even below if we stretch it to catch up with the miniaturization. For glues, we can print even finer. There's for instance, array of pairs of the dots that are printed with each with the single shot. Actually perfect, because you print 2 dots at the same time, and there is a right spacing between them, perfect to bring the die on top of it and realize the flip chip integration. So basically, we are ready to do in a sequential manner to print interconnects first and then print the dies. But as Jeroen was presenting for 3D printed electronics, there is no equipment, because the processes are so new, there is no equipment available to realize that. So we have to do it ourselves, at least for R&D setting, to validate our processes. And that's what we did. You see here an image of the high precision tool that we've been developing and still in development that enables, in a sequential manner, realize a flip chip integration of micro-LEDs in a way that first we print fine dots of interconnects, and then on top we transfer the dies, both done with the same laser source, but what is different, it's a carrier plate. First we feed with the carrier with interconnect, then we feed the carrier with MicroLEDs. That brings me to the last slide of my presentation, where I would like to share with you our roadmap for the technology that I've been showing to you. So zooming first into MicroLEDs, that's where our main domain is, deploying our technologies. For components that will be, and they will certainly be, smaller than they are now, I think we can realize the flip chip integration that I showed you, printing interconnect and then transferring dies for the component as small as 20 micron by pushing the limits of our printing technology. But as they get smaller than 20, their alternative bonding needs to be considered beyond classical flip chip. And we are already working on conceptual ideas for the for this, but there is a big leap to do already to catch up for the 20-micron dies. Next to it, as also introduced in the very first introductory video from the Brabant here, we are also working on adapting the fast CT and deploying it for yet another domain. MicroLEDs is light, yeah? The electronic packaging, hybrid integration. For integrated photonics is about optical connection. That comes with a very different and unique set of the precision. Just to give some words, for optical connection, one needs at least 200 nanometers, if not better, aligning precision of the component to component. So it's yet another extreme challenge, but that's what we like, solving the challenges. And well, this brings me to the very last slide. I would like to thank you all for your attention, and if there is room to answer your questions. Thank you.
Well, Gary, thanks a lot.
Sure.
I noticed there's also much excitement about quantum dots. And they got like the Nobel Peace Prize this year for chemistry.
Yeah.
And at the same time, I also read that Japan banned cadmium, which is like a white soft metal, in devices. How do you see that? Do you think that quantum dots can play a role in the future, also in MicroLEDs, to get like the vibrant colors?
Yeah, absolutely. And beyond just the vibrant color, it's just to enable applications, because well, MicroLEDs is, yeah, you can have a monochrome with one light, one color, but how to do RGB, yeah? If they are discrete components that I've been showing the trend towards miniaturization, if they are 50, if they are 20, this is already possible. I showed you some examples. But if they are as tiny as a couple of microns, then we are talking about different world. And their RGBs will be very difficult to realize. They will be grown monolithically on a wafer, most probably, and to make RGB, you add a quantum dot to color them, to enable the color. And there is only way, most probably, to enable extremely high precision and highly dense displays. So this is the given for specific applications.
Okay. Thanks for that. And again, applause for Gary, please.
Sure. Thank you.
Thank you.